Now, while you're probably familiar with trigonometric and exponential functions before coming into your Cal 2 class, there are a few functions that you're probably not familiar with because, well, the interesting things about them have a lot to do with derivatives. And so that's what I'm going to define right now. I'm going to define two functions: hyperbolic sine and hyperbolic cosine. And depending on who you ask, how you pronounce those, some say sin h, cos h, or sinh, cosh, but the name for each of those, the full name here is, self some room, hyperbolic sine and hyperbolic cosine. And the way they're defined, they are not defined explicitly in terms of derivatives and integrals, although you could also define them that way. The way I'll define them is simply in terms of exponential functions. And the hyperbolic sine is given by e to the x minus e to the negative x, all divided by 2. Meanwhile, hyperbolic cosine is e to the x plus e to the negative x, all divided by 2. And we'll go into some details of why these things are, maybe at first you don't think they have anything to do with sine and cosine. And they cannot be used in place of sine and cosine. They have different values most of the time. However, here's a good example problem. Let's just compute what their values are at 0. So the hyperbolic sine of 0 and what is the hyperbolic cosine at 0. So when you're dealing with hyperbolic sine and hyperbolic cosine, often it's just easiest just to go back to the definition. We'll definitely have to do that for this problem. So for the hyperbolic sine, we'll take sine h of 0 and use the formula e to the x. So instead of x, I have a 0 minus e to the negative x. So negative 0 is just plain old 0, all divided by 2. And, well, what's e to the 0? The exponential function at 0 is just the 0 power. That's 1. So 1 minus 1 over 2, that's 0 over 2. Okay, and hey, that's nice. The sine of 0 is 0. The hyperbolic sine of 0 is also 0. And what about hyperbolic cosine? Well, it's the same thing. It's just that you have a plus instead of a minus in the numerator. So I'll get 1 plus 1 over 2. And 2 divided by 2 is 1. So there's one of the first similarities between hyperbolic sine and cosine, because sine of 0 is 0, cosine of 0 is 1. Same thing for the hyperbolic versions. So that's it for that problem. Okay, what if it's a little bit more complicated? Here's another example problem. We're going to have evaluate the hyperbolic cosine of the natural log of 4. And the reason why we're involving the natural log here is because, well, we're dealing with exponential functions, and then things will cancel nicely. You don't need a calculator to do this. So let's compute. If it was sine, we'd have a minus, but for cosine, or hyperbolic cosine, we'll have e to the natural log of 4 plus e. Now don't forget, there was really a negative up here in this formula. It's just that negative 0 is the same thing as 0. Because up here at the original formula, it's e to the x plus e to the negative x. So I'll write e to the negative natural log of 4 all divided by 2. Okay? Now, well, what can I do? Well, let's see here. First part's easy. E and natural log are inverse functions. They cancel each other out, leaving me just a 4. But I have to be careful because I'm not going to get a negative 4 for this other one. That minus sign here means I can rewrite that as 1 over e to the natural log of 4, all divided by 2. And then I can cancel. I'm showing a little bit more work than maybe you would want to do there, but just to make sure everything's clear, my result is 4 plus 1/4 divided by 2. And that's going to be 17/4. Just write it here to the side. That's 16/4 plus 1/4 is 17/4 divided by 2. That's 17/8. So there is my final answer. So you can compute these by hand for numbers expressed in terms of the natural log, because the natural logarithm will cancel with the exponential function, e to the x and e to the negative x that are involved. Okay, so we've got cosine hyperbolic version of natural log of 4. That didn't have much in similar with the trig versions, but here's something that might look a little familiar. I'm going to prove one of the many, many properties of hyperbolic sine and cosine that are similar to the trig versions. I'm going to prove that the hyperbolic sine of 2x, this is like a double angle formula, but for the hyperbolic sine instead of the normal, and that's 2 hyperbolic sine of x cosine hyperbolic of x. And this should look familiar because it's exactly the same as the trig version. Just drop all the h's, and that's also true. But if we're going to prove this one, we're going to need to use the exponential functions involved. So what I'll do to prove this equality, I will just take both sides of the equation, sine hyperbolic, sinh, as some people call it, and I'll write the formula, but instead of x, I'll write 2x. Okay, and there might be ways to manipulate that, but that looks pretty simplified. So actually, I'm going to stop right there and take the right-hand side and see if I can simplify it a bit. So that's that. Now I'll take 2 sine hyperbolic x cosine hyperbolic x and write out its formulas. 2 times the fraction e to the x minus e to the negative x over 2, and another fraction e to the x plus for cosine e to the negative x, all divided by 2. And this is all multiplication, so 2 times the fraction times the other fraction, and so I can cancel a 2 on the top and bottom, and that's good because we're trying to make it look like that guy right there. The other thing I'm going to need to do, let's just combine both of those fractions, if we will. So I've got a fraction all divided by 2, and I'll write it out e to the x minus e to the negative x times e to the x plus e to the negative x. And what we'll need to do is we'll need to expand those binomials being multiplied together using, you can think of it as the FOIL method. And when we multiply everything out, what do we get? well, we'll get, I see e to the x times e to the x. That's e to the x squared. I see plus e to the x times e to the negative x. All right, minus e to the negative x times e to the x. And then the last two multiply together, negative e to the negative x, e to the negative x. That's going to be minus e to the negative x all squared. We'll divide that by 2, as it is on the line above. And I notice some canceling, which is nice. I cancel e to the x, e to the negative x. Here's the same thing but with a negative, so those cancel each other out. And the other thing I should notice is that what is e to the x all squared? Well, if you have two nested exponents like that, you can just multiply them together. That's e to the 2x minus e to the negative 2x. All that divided by 2. And hey, just a moment ago, what is e to the 2x minus e to the negative 2x? We saw that right up there. This is indeed exactly the same thing as sine hyperbolic, or hyperbolic sine of 2x. And that finishes that proof. There are lots of formulas similar to this. So the thing that we proved right up here, sine hyperbolic of 2x is 2 hyperbolic sine hyperbolic cosine. That's very similar to the trig version. There's lots of other versions that are similar to the trig versions. I'm not going to require you to memorize a lot of these, but it is good to be able to prove that these exist when asked. And it's all about just rewriting things in terms of exponential functions and then doing some algebra.